Let's go ahead and get started. So today we're going to go over a data level parallelism, which is the idea of being able to process multiple pieces of data at the same time, hence the parallelism. This is different than what we've talked about so far. With in-order pipeline and out-of-order pipeline, we've been talking about what's called instruction level parallelism, where you try to execute more than one instruction at the same time, or you try and pipeline them so you're executing different parts of the instruction at the same time. And that's called instruction level parallelism. With data level parallelism, you're going to have basically one instruction or maybe a group of instructions that operate on multiple pieces of data at the same time. So it's going to be a little different. And so here's what your GPU does. Can anyone guess what the next level would be after instruction level parallelism? Then data level, what would be the next more coarse-grained version? We can get this idea in people's minds. It's a tough question. No, don't go down, go up. So instructions at the bottom, data's a little more high level.
Spinning disks.
Spinning disks. So I guess the next one would be more of a thread level or process level. You'd have multiple processes happening at the same. Yeah, you have multiple data paths in your CPU, multi-core, namely, is what's going on. But this isn't quite multi-core because you're really operating on multiple pieces of data at the same time. You're not having multiple data paths. So if you can think about it in those three, where you have instruction level, data level, and thread level, the data level, you're just expanding basically your execution stage to be able to execute more at once, but you're not adding another execution path. But we'll get more into that. Introduction. Okay, the big thing, you're going to see SIMD here a lot. It stands for single instruction, multiple data. So you might have one instruction that tells you to do 4 additions or 4 multiplications, or maybe it tells you to do multiply and add as well. But it's one instruction that's going to operate on multiple pieces of data. And this is data parallelism because it's multiple pieces of data. Very good for matrix-oriented scientific computing, also for GPUs. Media is very good for media and image sound. I don't know if y'all remember MMX when it came out. That was probably the biggest standard addition to Intel. You probably remember that. Intel chips. But now we have SSE 1 through 4. Same thing, just different ways to go about it. We haven't talked about MIMD, but if SIMD stands for single instruction, multiple data, what do you think MIMD stands for?
Multiple instructions.
Multiple instructions. So that would be more of a multi-core approach. While this one's single instruction, you're still on a single core. Let's see, SIMD allows programmers to continue to think sequentially, which is nice because when we try and go into parallel processing, hopefully if you've taken my OS course, you'll notice that that gets very problematic very quickly. All right, different types of parallelism. SIMD is more of an umbrella of different types of parallelism, but it gives you the idea of having one instruction with being able to operate on multiple pieces of data. Pretty much the 3 most common ones, well, the first one used to be very common, is a vector processor, vector architectures, where you have a wide range, you're able to operate on a vector. Those are still used somewhat, especially in supercomputing. For most of our desktop applications, we use SIMD extensions, MMX, SSE4, that's what they're there for. But your GPUs or your graphics cards are huge SIMD machines, is essentially what they are. So was it, for x86, expect 2 additional cores per chip per year. SIMD width to double every 4, potential speed up, SIMD to be twice that from MD. What the author's trying to point out here is that since adding a core adds a lot of overhead, and we're especially going to see that when we go into cache coherency protocols. It ends up being that if you can keep everything on the SIMD level, you can take advantage of your hardware a lot better, if it's possible. Problem is that's only possible for so far. Okay, so first we're going to talk about vector architectures. Notice we have vector, SIMD, and GPUs. We'll talk about vectors first because that's pretty much came out originally, and I think it's one of the simpler ones to think about. But the idea is you're going to read a set of data elements into a vector registers. So you have basically wide registers, and you're able to operate on them, and then disperse the results back to memory. Registers are controlled by the compiler. They give you a nice picture. This makes it easy. All right, maybe not yet. So for example, MIPS came out called vector MIPS, loosely based on Cray 1. If you remember, Cray was the old supercomputers. Let's see, each register holds a 64 element, 64 bits per element vector. Think about that. So your one register is now 64 by 64. So it's a pretty huge register. 16 read register file has 16 read ports and 8 write ports, probably because you're trying to read all that in. You want to burst all that data. And the vector functional units are fully pipelined, do all the data control hazard, vector load store, again, pipeline, one word, and then your scalar registers were, as well, you have 32 of each of those. So keep this in mind. In addition to the standard 32 registers you had, 32 for integer, 32 for float, you're going to have 64 element vector registers as well. Give me a picture, not yet. All right. Add VV adds 2 vectors. Add VDS to add a vector. So here's an example. We load some value A into, looks like F0. Load the vector X into, oh, I'm sorry. Yeah, load D, so into F0. Load the vector V1. Vector scalar multiply, so this would multiply F0 by everything in F1 and send it back to F2. So notice that everything in that vector was good. Load vector V, now you can do vector multiply or vector add, and it would add all the elements as well, and you can store a result back out as well. So this is only 6 instructions as opposed to 600 in MIPS. If you think about it, what they're doing is with matrix multiply, you had a bunch of loops. They're basically breaking those loops down into individual instructions. Do we have a picture? Hold on a second. Here we go. Oh man. Nope, that's not the picture that's going to help. I lied. All right, we'll go with this then. Execution time. First off, the length of the operands, any structural or data hazards. They consume 1 element per clock cycle, so execution time is approximately the vector length. But what you're saving here right off the bat is you don't have to do that for loop at the end, check it, jump back up. You're not doing branching. All that's known ahead of time because you're basically encoding that whole for loop, so to speak, in a single instruction. So I can just execute all those multiplications really quickly. Something called a convey, a set of vector instructions that could potentially execute together in case you wanted to try and do multiple vector units at the same time. All right. Let's see, challenges, yeah, you gotta start them up. You have the latency of a vector unit. What is this, 6 cycles for an add, multiply, divide. A vector load is 12, okay. Yeah, the real issue here, if anyone caught this, is that if you don't have a 64 byte wide vector, this can get somewhat problematic, because if it's bigger, then you're gonna have to do multiple instructions. Which means you'll probably have to use some type of looping construct. But still, being able to at least encode 64 of these additions into essentially one instruction is very advantageous. Yeah, the last one also can be difficult because the compiler ends up not being too useful for this because it can't always detect what's going on. All right, we'll go ahead and go to the picture here. So the other advantage they have, notice that the first advantage is that you're encoding, hopefully you're encoding this for loop of 0 to 64, do this multiplication inside of this one instruction, and this is vector multiply, vector multiply, so this is, again, the for loop, 2 for loops actually, and one, oh no, it's add, never mind. It's add, so it's getting that whole for loop inside of one instruction. So you're being able to skip the branching, which is nice. Another thing that ends up happening is that since all those multiplications and additions are done independently on one another, aka they're not dependent, you could actually add a piece of vector hardware where you're able to do 4 of the additions or 4 of the multiplications at the same time. Because again, you've encoded the instruction. Yeah?
I got a stupid question, but how much data is in a vector?
So it depends on your architecture. For our example, we were saying 64 elements.
the 64 element register, that's one complete vector.
Right.
64 bits per element.
Mm-hmm.
And
So 64
elements.
doubles.
So that's.
It's a lot. Yeah, it's substantial, especially against your register file. That's what we're assuming for MIPS. Other vector machines have other numbers, but one of the problems, as I was trying to state, is that if it doesn't fit in that vector, you might have some other issues come along that you have to work around. But if you know how to code it correctly, it's actually gonna be fine. Yes, Matt?
No.
Okay. Right, so the next one is you have different lanes. So you could have, up here you have 4 lanes. They can do the first vector elements. This one's going to do every 4th one starting at 0, every 4th one starting at 1, every 4th one starting at 2, every 4th one starting at 3. And so that allows you to actually do 4 of these elements at once. Because if you remember with, if you think about vector addition, you don't have to, let me say this correctly. The additions don't depend on one another. They're independent or mutually exclusive. You can do them in any order. It doesn't matter. So the fact that you're doing these in parallel is just fine. And all they're doing is adding lanes so that you could do 4 of them at once, and it just keeps going until there's no more data to complete. You okay with this, Matt? Okay. All right, well, here's your question. Vector length may not be known at compile time. Well, you have a vector length registers, strip mining for vectors over maximum length. Yep, so what happens is that they'll have a vector length register that basically tells you how long the register is. You still have to encode your for loop accordingly, but you're able to actually do the vector loads and multiplies on the certain amounts. Y'all familiar with striping? So if you're let's say you can do 64 elements. Maybe that's this part, this part, this part, this part, dot, 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 dot. And then maybe your last one is 32 elements. That's fine. You've just striped it along so that you first operate on these 64 with the instructions, and the next one, then the next one, then the next one, so forth and so on. Okay. Any questions? That's basically vector machines. There's not too much. I'm not going to make y'all do a project on this, but it is important to understand where all SIMD originated from. All right.
Sure.
Sure. What does this sound like to you, Matt?
Spinning disk.
Hopefully you can tell with vector machines there's a lot of data moving around. And reading all that from main memory can be slow. So spread accesses across multiple banks, control bank addresses independently, load. What does this sound like? You have banks of memory, load or store non-sequential words, support multiple vector processors sharing the same
Sounds
memory.
like they're hoarding all the data.
In a what?
A thievy cache.
Yeah, a thief cache. That's what we should call it, a thief cache. Yeah, so you gotta bank it again, make special caches dedicated for vector machines. All right, seriously, guys. Good. All right, we're done with that. Unless I'm really not going to go into vector machines much more than that.
Okay.
Yeah, they're not. You got the idea. That's about all we need to go into, because now with SIMD, this is actually a far more pragmatic approach that I've found. We still use vector machines, but this is more of what you're going to encounter. Okay, so let's see. Media applications operating data types narrower than the native word size. Do you all have any idea what that means? How do you do colors in computers?
RGB.
RGB. How how much value do you store in each of those RGB? It's actually RGBA, but depending
What
on
is it? It's like 4 bits times 8. 32 bits.
yeah, but how many is in R?
Oh, I don't know.
Usually about 8 bits. Then G is also 8 bits. And then B is also 8 bits. And I know, Matt, it's too hard to find this pattern.
16.
Yeah. Sometimes with 8 bits as well. Right? So if you want to do some calculation, well, that's 8 bits. How many bits is in there? 32, which is inside of an integer register, which is handy. But there are 8 separate numbers contained inside that 32-bit register. So what the original SIMD did is you were able to basically treat the integer registers as a color value, 4 separate 8-bit integers. Excuse me. And then do different operations: add, subtract, multiply, divide. Right, Matt? Yeah. Number of data operands encoded into opcode. No sophisticated address. Right. No mask.
No mask registers.
Yeah, no mask registers. You know what a mask is? So let's say your number did not have alpha, and then you want to mask it. Oh, wow, what that was.
Q.
Red, green, blue, alpha. So if you take whatever this is, and then you ampersand it, and it with this, you're masking out the alpha, is what you're doing. Right?
Mm-hmm.
Okay, so first off, MMX in 96. You remember that, right?
Sure.
8-bit integer ops for 4 16-bit operations, so they were able to do it on 64, basically 2 registers at the same time. Whoa. Streaming SIMD extensions, SSE. What we got? Yeah, 8, 16, 432. There's SSE 1 through 4. Basically, they just added it for floating point doubles and then added a couple other things, is what they've done. Advanced vector extensions for, extensions. Extinguishes. Extensions for 64-bit integer floating point ops. Okay. Hopefully you can see that they must be consecutive and aligned in memory. So it has to be, your data has to be partitioned out in a very specific way. All right. Everyone ready? Matt, tell me what this code does.
It gives you the derivative of Python.
What is the derivative of Python, Matt?
I don't know. We'd have to run the code.
What's LD?
Load.
Load.
Double.
Double, yeah. There, good guess. And then we're making copies. Wow, DADDIU. I don't even remember what that does. Let's go ask the interrupts.
Add double
With the 5
integer
power.
unsigned.
Yeah, integer unsigned. I got that one. I completely forgot what this one does. Yeah, it's double add integer unsigned. That's got to be what it is. Right? Doesn't that make sense? Double D for double
Yeah, I think I have
add.
to look it up.
Wow.
Last.
You know what's cute is this. It's not coming up. Oh, here we go. You'll be
This
hilarious.
PDF is older than me.
When were you born, Matt?
October 95.
Oh. Is that why you don't remember any of this?
Yeah.
I want to work on that, Matt.
Pretty sure that's why.
It says it found 6 of them. Forums. That's great. All right. Double add immediate. Okay.
Immediate.
Immediate. So it's going to
Takes the
add,
value.
whoops, it's going to take 512, add it from, it looks like a base address into RX. Wait, which one is RX? Yeah, that's the, so yeah, it goes into RT. So it's going into RX. There we go. So they're finding the base address for RX, loading it in. Okay, great.
So it goes into RX. This is what always confuses me.
Yeah, because they always rearrange it, don't they? Yeah.
Mhm.
Yep. That's how they do it. Don't know why. I tried to keep it simple with our instructions. I can't force other people to make it simplistic. I can only do what I can. Oh well. All right, loop. Load.
Oh, class
Oh,
is over.
classic. For those of you online, we have lost connection.
Send help.
And we need to put in a help ticket. That'll work.
Oh, didn't have. Just call Matt.
All right, looks like we're taking a break until this fixes itself.